My name is Ref. I'm a physics master's student here at Brown University. And today, me and my team are going to discuss this satellite mission that we've been developing for the last year, known as the T-REX mission, the Time Resolving Explorer mission. And the primary science objective of this mission is to capture the first time-resolved video of the accretion disk of Sagittarius A star, or colloquially speaking, to capture the first video of a black hole. The goal of this presentation is to give a kind of overview of our primary science objectives, our key mission parameters, and what our timeline and funding looks like. We have several of our co-Is joining via Zoom, and they're going to be also discussing our engineering constraints and our secondary science objectives. So without further ado, let's get started. So I've broken down this presentation into 10 parts. First is an introduction into the scale and scope of my team and what we're trying to achieve here. I was not sure what the background of the audience is going to be, so I'm going to give a very quick preliminary sketch of the key geometric features of a black hole we're seeking to image. And then we'll discuss how the EHT imaged a black hole for the first time and how BEX, the Black Hole Explorer mission, hopes to image a black hole, M87 and Sagittarius A's photon ring. And then we'll move on to recording a black hole. How do you capture a time-resolved movie of a black hole, as it were? We'll then move on to T-REX's primary science objectives, its UV coverage. Our students here are going to discuss the plots we have for the UV coverage, several of the engineering challenges we foresee by virtue of a low Earth orbit, our preliminary swap requirements, our concept of operations, and timeline and funding. So first, let me begin off with an introduction into me and my team. The elephant in the room is, what is a master's student doing leading a satellite mission proposal? And hopefully the scale and scope of what we're trying to do is going to become clear in the next few slides. Let me preface everything by saying that all of our work over the last 8 months has been student-led, but now we are really trying to obtain a faculty co-PI from the EHT or VLBI or radio astronomy communities to advance the mission further. So this is my own background. My name is Ref. I'm a physics master's student here at Brown. I work under Professor Brendan Keith on NASA's LISA mission. I'm funded to create radiation reaction models for LISA. And in my spare time, I work with Brown's satellite development team, which has the following spaceflight heritage. These were all low Earth orbit CubeSats, which were funded by NASA's CubeSat launch initiative. So essentially, NASA pays Brown about $300,000 to test low TRL technology in low Earth orbit. And so back in January, I proposed this idea of a low Earth orbit satellite that could capture a time-resolved movie of a black hole, as it were. And so that is the idea behind T-REX, the time-resolving experiment satellite. The primary science objectives are threefold. First is to capture a movie of M87 and Sagittarius A star. I'll make the technical requirement behind this clear in a moment. The secondary science objective, which Andrew from the LIGO collaboration is going to discuss, is we seek to time resolve binary black hole systems that are radio loud around 86 gigahertz, like OJ287 and several other targets. And finally, Dr. Crystal Lynn Smith and Travis Fisher are interested in using T-REX for time domain astronomy in the millimeter wavelength regime, as I'll discuss in a moment. The key idea behind capturing a video of a black hole is as follows. What do I mean by capturing a video of a black hole? What I mean is the following. Sagittarius A star has this accretion disk around it, hot dust, gas, and plasma that's orbiting the black hole. Now, if you'd like to capture a video of this black hole, then what you have to do is you have to take pictures of the black hole on shorter than 30-minute timescales, because the timescale of the accretion disk at ISCO, if this is a short shell black hole, is about 30 minutes. What does that mean? That's a lot of words. What it means is that if Sagittarius A star is not spinning, if it's a stationary black hole, then at the innermost stable circular orbit, it would take matter about half an hour to orbit the black hole once. By the way, if there's any questions or any strong objections or concerns, please raise them before the NSF does. So this is what I mean by capturing a video of a black hole, and I'll make the technical requirements clear in the following slides. Now, the T-REX mission, we envision it to be a core component of the decadal survey as follows. NASA's decadal survey outlines the key priorities for NASA for the next 10 years. And so T-REX would fall under the time domain astrophysics program, um, with which NASA hopes to analyze multi-messenger events. The key swap requirements for T-REX are as follows. It would be, these are preliminary numbers, but the satellite would be a small sat, bordering on the edge of a small sat, weighing in at about 100 kilograms, consuming about 500 watts of power, and costing about $30 million. So this would fall under NASA's time domain and multi-messenger astronomy program. And in particular, it's this class of mission, NASA Astrophysics Pioneers Program mission. NASA, every 4 to 5 years, sends small sats up to the ISS with a cost cap of about $30 million. So this is ideally where T-REX would fall under. Currently, our mission is in the pre-phase A stage of NASA's life cycle development. So we envision it to stay in the pre-phase A and phase A stage for the next 4 to 5 years. And what we're really hoping to do at this stage is, now that we have some preliminary background on our proposal and swap requirements, we're trying to obtain a faculty co-PI from the EHT or radio astronomy community. These are several of the grants that we've applied for in the last year. The NASA NIAC solicitation, the Templeton grant, and we're working with several Canadian institutions on a FAST grant. Recently, we were selected by NASA as a finalist for the $175,000 NIAC grant, and so we're working aggressively with our partners to submit this by October 7th. And we were also invited to the International VLBI conference in Sweden to present T-REX there. So now let me briefly illustrate the scale and scope of the team. As I mentioned previously, this has been a student-led initiative since day one, but recently, by virtue of our kind of preliminary proposal being completed, we are now trying to obtain co-PIs from the EHT community. Several of the folks who are engaged with the project right now are at Princeton, several Canadian institutions, our advisors, and the T-REX team. Let me go through this. So Princeton Space Physics Lab is a recently established department under the physics department. They have worked extensively on NASA's heliophysics missions, and they're just wrapping up their work with the IMAP mission. They've also worked on the Parker Solar Probe, and they're interested in working on one of T-REX's subsystems on our NIAC grant. In terms of our Canadian partners, we have Luke Anderson on the call with us from Orion Space Systems and also at Utah State University. Laura Locke and Jay Shree are all professors in Canada who are interested in working with us on the CSA FAST grant for T-REX. And then in terms of our advisors, we have Rick, Travis, Krista, and Andrew. Travis and Krista couldn't be here today, but they've contributed a slide here, which I'll show in a moment. Rick is an engineering professor here, and Andrew will be discussing the multi-messenger capabilities of T-REX in a moment. And finally, we have the T-REX team itself. If you guys want to introduce yourselves.
Hi, my name is Noah. I'm a master's student here at Brown, and for our team, I've been doing a lot of the theoretical work, things like constraining variables of interest.
Hi, I'm Shirani. I'm also a master's student here at Brown, and I work on. Hi, everyone. My name is Kaylee. I'm a sophomore here at Brown. I've been helping with a lot of the
I'm Sebastian. Actually at Columbia, so not here. But so I took a bus this morning. Yeah, it was a good ride home. But I'm currently a master's student studying mechanical engineering, and so I'm focusing mostly on building the actual satellite buses.
Hi everyone, I'm Graham, in undergrad studying engineering at Brown, and I'm an undergrad engineering lead with the team and have been mainly focusing on data outline.
Hi, I'm Mia Perkey. I'm studying background here at Brown. I'm an undergraduate, and I'm one of the student science leads here. I've also been focusing on thermal noise and dynamic energy.
Okay, sweet. So now that we have a scale and scope of the team, I didn't know what the audience background would be, but I'm going to very briefly, to ensure everyone is on the same page, discuss what are the key geometric features of a black hole, and how do we image a black hole. So the key geometric features of a black hole are its event horizon and singularity. If we trespass the event horizon, we're doomed to fall into the singularity. If we zoom out a little bit, this is all relevant for a Schwarzschild non-rotating black hole, not for a Kerr black hole. But at 1.5 times the Schwarzschild radius, we have the photon ring, which in 3 dimensions becomes the photon sphere, which is what the Beck's mission is trying to directly image for the first time. If we zoom out further, we find the black hole shadow, and zooming out even further, we find the innermost stable circular orbit. This is the last orbit that anything with mass can orbit the black hole. And so where do all of these geometric features come from? They're all described by a single equation, the Schwarzschild metric. And if we write down the conservation of energy from that and draw the effective potential, the photon ring comes in as the unstable orbit for a massless particle around a Schwarzschild black hole, and ISCO comes in as the stable orbit for a massive particle around a Schwarzschild black hole. So if we put all of these together and see what it looks like, this is what it means to have a black hole shadow. In the first image of a black hole, this shadow that we're seeing here is really this critical curve where if you throw in photons at just the right distance from the event horizon, they curve in and they just graze the photon ring, and then they head out back to the observer at infinity. Great. So now I'm going to very briefly discuss how we image a black hole, just so everyone's on the same page. Imaging a black hole requires radio telescopes rather than optical telescopes. And this can be seen from the spectral energy distribution of Sag-A, for instance. This spectral energy distribution tells us where the black hole is loudest, as it were. Where does the black hole emit most of its flux, most of its luminosity? And we can see that's mostly in the radio regime. But there's also another reason to observe in the radio, and that's because the Earth's atmosphere blocks most wavelengths of light, except for optical and radio. And so those are 2 key reasons we need to use radio telescopes to observe black holes. But there's an added complication, several added complications, of course. First is, how far apart do you have to place your telescopes? And that comes down to angular resolution. If you'd like to image Sagittarius A star, it spans about 50 microarc seconds. To put that number into context, that's similar to trying to take a picture of a donut on the moon from the Earth. So it's very, very difficult to do because it's a very compact object. And so you need to put telescopes very far away to achieve the angular resolution required to resolve Sag-A. But now there's another problem, which is that there's a lot of things between the black hole and your telescope. Specifically, there's interstellar scattering, which can take an image like this at 86 gigahertz and completely botch it out. You can no longer resolve the ring-like structure, as it were. This is from one of the EHT papers. And finally, to cap it all off, you have to think about what parts of the atmosphere are most transparent above your observing site. So for example, this is the atmospheric transmission above ALMA, the most powerful radio telescope array in the world. And as you can see, ALMA, you would ideally like 100% radio transmission. That means that all light passes through the atmosphere. 0% transmission is bad. So here's what you see. At high observing frequencies, the atmosphere blocks a lot of the light. But there's a kind of cost-benefit analysis to be had here, because as you go to higher observing frequencies, interstellar scattering decreases. So at higher frequencies, this becomes less bad. But you can also see that at higher frequencies, the atmosphere gets more worse. So this forces you to put a telescope into space, as it were, not only to achieve the angular resolution required, but also in part due to the atmospheric constraints. So now I'm just going to very briefly discuss the UV plane. How does a radio telescope capture an image of a black hole? Well, it samples the strength of the electric field near the black hole target. So if I may borrow an analogy from Michael, these ducks can teach us a lot about how to take a picture of a black hole. So what we're trying to do here is solve an inverse problem. We're trying to figure out can we figure out the distribution of ducks in the pond from the oscillation at the edges? And the answer is yes, with an asterisk mark. If you just stand on the edge of the pond and you measure the oscillations at the edge, you'll only be able to tell the total intensity, the total amplitude of the oscillations. So you'll only be able to tell what are the total number of ducks in the pond, but you won't know what their distribution is. Now, for physics majors, this is hard, but you need a friend so who you can compare your observations with. And so what we're really trying to do here is compare the oscillations that observer 1 measures with observer 2. And in the language of quantum field theory, we're computing a 2-point correlation function. We're trying to calculate the correlation between the electric field intensities measured by telescope 1 and telescope 2. So this is the basic idea behind the Event Horizon Telescope. It's a collaboration of 10 or more telescopes around the world that all compute this 2-point correlation function and thus sample the black hole on this Fourier domain. And the key idea is that the more you can sample the black hole on this Fourier domain, the better your reconstructed image quality of the black hole. You can see that as the UV coverage improves, so too does the reconstructed image quality. Okay, great. So that brings us to how the EHT captured the first image of a black hole. And the Black Hole Explorer satellite mission, the BEX team hopes to capture the first direct image of the photon ring around the black hole. And to do so, to achieve the angular resolution required to directly image the photon ring, you need to go all the way out to medium Earth orbit, where the angular resolution is about 5 microarc seconds. So this is the idea behind EHT and BEX. And so now that brings us to how do you record a black hole? And so that brings us to our proposed satellite mission, T-REX. So what do I mean by recording a black hole again? What I mean is we'd like to temporally resolve the accretion disk structure around the black hole. And by doing so, as Noah will inform us in a moment, we can constrain the spin of a black hole by figuring out how fast the hot spots move around the black hole. There's several other interesting things we can determine, including the magnetic field strength around a black hole, but Noah will take over that in a moment. Now, the key technical requirement to temporally resolve a black hole can be found in one of the EHT papers by Daniel Palumbo, in which they outline this criteria to temporally resolve Sagittarius A star. To resolve the accretion disk of the black hole at the center of our Milky Way, we need at least 50% UV coverage on sub-ISCO timescales. And so in terms of, okay, well, never mind. Now that brings us to our primary science objectives. So the threefold primary science objectives of the T-REX mission are as follows. First, we seek to capture time-resolved videos of M87 and Sag-A. Andrew Miller will be discussing how we seek to temporally resolve binary black hole systems. And finally, Dr. Fisher and Smith are interested in rapid time domain observations of quasi-optical outbursts and other transient targets using T-REX. So to first start off with our primary science objective, again, this comes down to this key plot. This plot, I'm going to explain this plot right now. So what are we looking at here? This first plot is showing the UV coverage of the Event Horizon Telescope in a span of 30 minutes. Again, 30 minutes is the critical number for the time scale of the accretion disk of Sagittarius A. And you can see in the span of 30 minutes, EHT has about 20% UV coverage, observing at 230 gigahertz. Now, if we add just one satellite in low Earth orbit, the key idea is that this doubles the UV coverage up to 56%. And the key reason why is that adding a low Earth orbit satellite rapidly increases your UV coverage by virtue of these long tracks on the UV plane from the space ground baselines, as opposed to these much shorter tracks from the ground baselines. Now, this is at 230 gigahertz. Our proposed satellite would be operating at 86 gigahertz, but the key idea is that 86 gigahertz, as we understand it, the only thing that would change is the spatial scales that we would be sampling would be shrunk by a factor of 3. So our UV coverage would likely remain the same, around 56%, but the part of the black hole that we're adding UV coverage would be closer to the origin of the UV plane. As opposed to 230 gigahertz. So in terms of reconstructed image quality, this is what it looks like. This is from the same paper by Daniel Palumbo. If the EHT, if the Event Horizon Telescope observes Sagittarius A star for 30 minutes, this is what a simulated observation looks like with 20% UV coverage. But adding just one satellite in low Earth orbit enables you to begin tracking hotspots around Sagittarius A star. Again, all of these simulated observations are operating at 230 gigahertz. And so at 86 gigahertz, the reconstructed image quality would, of course, be different, especially after accounting for interstellar scattering. But we have some basic simulations of that I'll show in a moment. So now Noah will discuss some of the science, some of the physics that we can learn from taking a picture of a black hole video.
So even in the case of a still image, you actually can learn some stuff about the spin of the black hole, although the constraint on the spin will be weaker than usual than in the case of a video. So what you can do is you take photons that basically barely graze the black hole, they rotate for a while, and then they project under our image plane back at Earth. And what you'll see is this characteristic, almost cardioid-like shape, and that will be the shadow of the black hole. So in the case of a non-rotating schwarzschild black hole, this will look like a circle, but in the case of a curved black hole, we were able to constrain both the spin and the mass this way. And these are called coordinate coordinates. It's just how you do it.
You can just.
But of course, we'd be taking a video, so what we'd be seeing is different patches of bright and dim, and we'd be seeing flare-ups, and so you can actually look at those, and those would be periodic flare-ups, and using that, you can further constrain the spin, as well as some other variables here. So m dot here is our mass accretion, so or accretion rate. So it's one of the many things we're interested in, including polarization and magnetic field strength and luminosity. And so you can see as sort of the back of the envelope thing, the Keplerian orbit scales as 1 over an R quantity. So this means that matter closer to the black hole will be spinning faster, and that creates a lot of friction, which means heat. And so the matter around the black hole is actually this low density plasma, so it's the soup of electrons and protons. And if you'll excuse my drawing quality, I outline here some of the process that goes into the jet of the black hole. So essentially we have our rotating ionized plasma, and this creates, due to the what's called the dynamo effect, a toroidal magnetic field. So you have almost this donut shape that goes around the black hole. But then, of course, we have these very intense gravitational effects. So since the black hole's spinning, we have what's called frame dragging, and you can essentially think of that as space itself kind of rotating. And what that does, when you include these two effects, is it twists the magnetic field in the direction of spin. So if it looks something like that, it wouldn't be as neat, obviously, but yeah. And so with that magnetic field, this, of course, then creates, due to Faraday's law, a displacement field, which you can think of as like another electric field, basically, which would be going in that direction of spin. And because of that, the electrons and protons in the actual plasma will want to move along or against that. So the heavier protons will move with the field, and so the field sort of wraps, this displacement field wraps around the accretion disk. But of course the electrons are a lot lighter, so that contributes to most of the actual flux density. So that those electrons will travel up against the displacement field, and that's at least partially an explanation for why you see this jet. And with our video, we'd be able to make a lot of constraints. Of particular interest is the ratio of temperature of the electrons to the ions, and then of course the power of the actual jet, which is proportional to the spin squared.
Nice, thank you. Okay, great. So that brings us to our secondary science objective, which is T-Rex hopes to time resolve several binary black hole targets such as OJ287. So that takes us to Andrew Miller, postdoc from the LIGO collaboration. Andrew, if you want to take it away, I think screen sharing should be enabled now. Yeah, capabilities that T-Rex could have. That being said, we would have to target binary systems that ideally would suffer less ISM scattering because we are operating at 86 gigahertz. And also we'd probably have to look at systems that have orbital timescales that are within the temporal resolution of our telescope. But yeah, okay. And the final primary science objective for the T-Rex mission, okay, this is Andrew's part, is to conduct a VLBI survey of active galactic nuclei targets at 86 gigahertz. What does that mean? These are some of the secondary science targets for the BEX mission, but Dr. Travis Fisher and Crystalline Smith are interested in T-Rex for the following reason. They contributed this slide. I don't have a full understanding of their interest, but essentially they're interested in AGN targets and quasi-optical outbursts that have variability on the time scale of T-Rex's temporal resolution, so about 30 minutes. So these could be blazar or quasars that are evolving over minutes or hours. And so they pointed out that really at this point in time, there is no telescope that can conduct time domain astronomy in the millimeter wavelength regime at 86 gigahertz. And so this would be in concert with ALMA Band 2 and potentially IRAM. MIT Haystack and Green Bank can also operate at 86 gigahertz, so those are also potential co-observing telescopes. They're also interested in creating potential temporal light curves of these quasi-optical outbursts, but they can speak to this more than I can. So, okay, finally, we arrive at what is potentially the most critical part in terms of science, which is how much radio coverage does our telescope have? And so what I mean by that is how well can we cover up the UV plane? So to speak about those results for M87, Sharania will discuss her results.
Hi everyone, so what I'm going to talk about here is what you see here is the UV coverage we get for one of our targets, which is 7, and each of those plots are combined with our ground-based EHT telescopes, along with our close TX satellite and observing at the.
Oh, yeah.
Okay, so what you see is each of these blue baselines here is basically showing the T-Rex along with individual EHT telescopes, and then the gray points that you see around here is just the ground. And this basically shows us which Fourier components of the black hole image are. So each of these plots actually are on a time scale of about 30 minutes, and then on our x-axis here, you will see that our spatial time scale is about 6. And just as a reminder that this whole UV plane is basically a Fourier transformation of the source intensity that we're trying to get. So the way to think about that is that the center of this plot, which is closer right here, the shorter baselines, they correspond to the larger environment of the black hole, so more of like the accretion, extended accretion flow. Whereas as you move outward on the UV plane, you get the more detailed detailed inner parts of the black hole, so we move more towards the black hole shadow.
Thank you, Sharanya. Okay, great. And so that's M87, which was the first target for EHT by virtue of its longer time scale for its accretion disk. M87 is 1,000 times larger, and thus it's the orbital time scale for M87's accretion disk is about a month. So it's not as difficult to create a video of M87. And in fact, next generation EHT should be capable of doing so in about a decade. But really, the kicker here is Sagittarius A star, which and Kaylee is going to discuss her results for Sagittarius A star's UV coverage. And by the way, this plot is taken from Bex's hybrid observatory paper, but yeah, Kaylee, you can take it away.
Hi everyone, so like Ruff just said, this is from a Bex paper on operating a hybrid observatory published in 2020. So for the sake of brevity, what you see here and what this tells us are the optimal times of year for our satellite to be observing these science targets, M87 and Sagittarius. So Sharanya showed her simulations, and optimal coverage for M87 star happens in the winter months, and so that's what her simulations were for. Now for Sagittarius A star, it's in the summer months. But to note, when we ran these simulations, we ran it for every month of the year and various times of the day to verify that. And what this comes from are various factors such as time of day that the telescopes in the EHT array would be observing these targets, as well as factors that have to do with Earth's atmosphere, because as we've talked about, that does affect our coverage that we get. So coming to our radio coverage, T-Rex co-observing Sagittarius A star with the Event Horizon Telescope. So these are our optimal results for June 1st. This is at 86 gigahertz observing frequency on a time period of 30 minutes. And so our optimal coverage came at 10:15 and 11 a.m. respectively. And you can see right off the bat, our spatial scale is a little different from the plots that Rep was talking about with the EHT co-observing with one LEO satellite. That was on the order of 12 gigalambda baseline length, whereas these are on the order of 4, so decreased by a factor of 3. However, the amount of UV coverage received is the exact same. The fill fraction that was on the EHT plots was 0.56. It is the same for these plots as well, meaning that we do meet the constraint of greater than 50% UV coverage on sub-ASCO timescales. However, the region of Sagittarius A star that we're sampling, as Rep brought up and Sharanya brought up the concepts as well, the region that we would be sampling on the shorter baseline length scales are those larger scale features of the black hole. So not the photon ring, but the accretion disk dynamics and relativistic jet outflows, which is our primary science objectives. And 2 points I'll add on to build upon what Sharanya was talking about. First, the concept of sparsity versus density in these plots and what that means. So for a faster moving satellite, such as T-Rex orbiting at Leo, the amount of UV coverage, the magnitude of UV coverage we'll be getting will be greater, but it will be more sparsely located on the UV plane, and that's simply because the orbital velocity of a Leo satellite in low Earth orbit is going to be greater than a satellite in middle Earth orbit, for example. For a satellite in middle Earth orbit, a slower moving satellite, the amount of UV coverage will be lower in magnitude, but it will be more densely located on that UV plane. Again, that just ties back to what regions of the black hole we're sampling and what your objectives are within that. And the second most important note is that these figures do not account for the amount of scattering light we're getting from Sagittarius A star will face as it's traveling to our satellite. That's very important. Rep touched on that, but he will also speak to it a little bit more. And that just means that we're not accounting for ISM scattering and interstellar medium effects, but Rep is going to add on that.
Thank you, Kelly. Okay, great. So those were single frequency observations of both of these black holes. Now I'd like to point out a key idea in the trade space. What do you gain by going to higher orbital altitudes? And the idea is very simple, okay? There's two key numbers we're trying to compare. We're trying to see what is our temporal resolution, how quickly can our satellite take pictures of the black hole, and what is our angular resolution? Essentially, how good is our picture of the black hole? Now, angular resolution and temporal resolution are both a little bit like golf. The smaller they are, the better. If temporal resolution is small, that means you can take pictures very quickly. If angular resolution is small, then you can localize the location of the radio target very precisely. So temporal resolution, a very back of the envelope estimate from a paper by Ben Hudson and Aditya Tomar can be given by the orbital period of the satellite divided by 4. And the angular resolution scales as the distance of the satellite from the Earth. So what you see here is, as the satellite gets further away from the Earth, the angular resolution gets better at the expense of the temporal resolution and vice versa. So this is a very back of the envelope way to kind of get a gauge for how these parameters are changing. And in particular, if we run the UV coverage simulations for a low Earth orbit with a semi-major axis of 6,000, an intermediate orbit of 13,000, and a medium Earth orbit of 26,000 kilometers, we can see the temporal resolution decreases or increases from 22 minutes to 3 hours from Leo to Meo. What does that mean? That means that essentially it will take 22 minutes for a low Earth orbit satellite to take one picture of the black hole and then stack those pictures up into a video. This is a very hand-wavy way to describe it, but that is the idea behind temporal resolution. Angular resolution, however, gets better from 35 microarc seconds to 6 microarc seconds at medium Earth orbit. So this is the kind of cost benefit we gain from higher orbital altitudes. And now I'd like to show some very preliminary simulations on multi-frequency observations using T-Rex. So what are you looking at here? This first plot is essentially just Cayley's plot of Sagittarius A star, observing Sagittarius A star for 30 minutes using T-Rex and EHT, both co-observing at 86 gigahertz. That's the first plot. But in the second plot, next generation EHT should support a tri-band of frequencies, 86, 230, and 320 gigahertz. So we have T-Rex and EHT co-observing at 86 gigahertz, and then EHT operating by itself with ground-ground baselines at 230 gigahertz. And finally, in this final figure, we show T-Rex, EHT, and BEX co-observing at 86, 230, and 320 gigahertz. I'd like to say right now with an asterisk mark that T-Rex will not support multi-frequency. It does not have a dual band frequency. It will only operate at 86 gigahertz by virtue of the fact that it is very difficult to observe at two frequencies simultaneously, as BEX will do. Now, if we repeat these simulations from 30 minutes to 60 minutes to 24 hours, we can see how the UV coverage improves over time. You have something like a Russian doll scenario here, where the 86 gigahertz coverage gets embedded within the 230 gigahertz coverage, and similarly as we integrate over 320 gigahertz. So finally, if we sequence all of our images of a black hole together, then we would ideally get a video, a time-resolved video of the accretion disk of these black holes. By the way, this is not our simulation. This is taken from the Event Horizon Imager team from ESA. So okay, so now that brings us to the engineering challenges for the T-Rex mission. And so, of course, there are many engineering challenges of a LEO VLBI satellite, but I've broken them down into some advantages of a low Earth orbit satellite and some disadvantages. So let me just rapidly run through this, and then Luke can come in during our swap requirement stage, or Luke, feel free to interject at any point if I'm bludgeoning any of the engineering constraints. But the first benefit of a low Earth orbit satellite is what we pointed out already, which is that we have rapid but sparse UV coverage, as illustrated by Kelly and Shirani's plots for M87 and Sagittarius A. Now, at 86 gigahertz, we would primarily be sampling the jet-like features and the accretion disk of a black hole. And so that's what you see in these simulations that don't account for ISM scattering. And so at 86 gigahertz, again, we would be adding UV coverage closer to the origin of these plots. From low Earth orbit, we also have decreased signal loss, but this is not necessarily an advantage because of the fact that at low Earth orbit, we also have limited ground coverage, as Graham Neely will discuss shortly. So this is an advantage, but not really, because by virtue of the fact that we don't have as much time to send down our data, our signal may need to compensate for that. There's also a decreased radiation environment in low Earth orbit, but again, this is an advantage that comes with an asterisk mark by virtue of the fact that a low Earth orbit satellite has to deal with significant atmospheric drag and tonic oxygen, as Luke Anderson will discuss. Now, ISM scattering, this is something that, Michael, of course, you have expertise on. We looked at Ben Hudson and Aditya Tomar's paper on ISM scattering for BEX. And I reached out to Ben and Aditya to ask if they could guide us on reproducing these simulations for T-Rex. And so when I did that, this is what we got. So what are we looking at here? This is T-Rex and ALMA co-observing Sagittarius A star with an intensity alpha parameter of 1.38. And what you see here is that everything in gray here is gray because that's where our observations would fall above the thermal noise floor of 10 millijanskis. So essentially, anything that's gray here, we cannot access. The next part of this simulation would be to overlay the UV coverage of T-Rex and ALMA co-observing. I haven't had time to do that, but essentially, the key takeaway of this plot is that even if T-Rex co-observes with ALMA, it can only access the largest scale structures of the black hole, which correspond to the smaller scale features of the UV plane. So this would correspond to, for example, the accretion disk or jet-like structure of the black hole. As you can see, there is no hope, obviously, of T-Rex resolving anything close to the event horizon or the photon ray. Not only because we don't have the angular resolution, but ISM scattering would destroy it completely. So really what this simulation shows is that after accounting for ISM scattering, even if T-Rex co-observes with ALMA with the lowest ISM scattering parameter of 1.38, we would be limited to time resolving only the accretion disk or jet-like features, if there is any, of Sagittarius A star. Again, all of these simulations are very preliminary. This is, as I've said, a student-led group, and we are hoping to obtain faculty to help support us in further developing these things. Okay, now there's one feature, a unique feature of T-Rex that I would like to bring that is contingent on co-observing with a MEO radio satellite, and that is a potential dual baseline capability. If T-Rex is able to co-observe with another satellite in MEO, then what we would have is a kind of dual sandwich architecture as follows. With our longer baselines between the MEO satellite and the LEO satellite, we can add UV coverage to stuff that is closer to the horizon scale structure of the black hole target, so further out from the origin of the UV plane. And with our shorter baselines, we can probe high flux density targets, things like the accretion disk or the jets of these black hole targets. And so this dual baseline capability would afford us this kind of best of both worlds. We would see both, we would add UV coverage to both horizon scale targets and be able to resolve more larger scale morphologies around the black hole. This is an orbital configuration that Ben Hudson and Aditya Tomar were exploring in their ISM scattering paper, where the Beck satellite begins in low Earth orbit and Hohmann transfers to a medium Earth orbit. And this is potentially interesting because if T-Rex is successful and the Beck's mission does opt for this orbital configuration, then you would have two satellites simultaneously co-observing from low Earth orbit, which can potentially assist with the temporal resolution and assist with ISM scattering. But this is, again, very preliminary. A significant problem that we have to deal with is infrared thermal emissions from the Earth. This is a problem because we are closer to the Earth than Bex will, of course, be. So this is a 3D model of T-Rex, which shows how we've attempted to mitigate this problem. Sebastian, in a moment, will be talking about the 3D CAD model and how he designed the secondary reflector for the antenna. But to mitigate the problem of thermal emissions from the Earth, we have these concentric circular antennas enveloping the primary antenna. So that takes us to limited ground coverage. So let's see. So Graham, if you'd like to discuss our problem with sending data down to the Earth.
So one of the most difficult problems with observing a black hole is that you generate an enormous amount of data. So once you've gone through all the scientific and engineering challenges of actually collecting the bare amount that you can get, you have to figure out how to convert that into data and get it back down onto the Earth. Because we're talking about petabytes of data, it isn't really feasible to hold it all up in space. So as it stands, we're looking at optical communication, either directly to the ground or in space links to a relay satellite that will then feed all of our information down to the ground. Now, going directly to the ground has the problem of we really can't see very many ground stations for very long. This is a plot of the ground tracks of the satellite as it orbits the Earth. And by nature being so close to the Earth, we're only going to pass through those areas of visibility for a very short amount of time, on the order of like 20 minutes in a day. Now, this could be mitigated by finding other ground stations and adding dots to these maps. However, that needs more collaboration, that needs more equipment and infrastructure on the ground. Now, one of the potential shown here is that the data is stored at least partly on the satellite using small SSD buffers on the order of a couple terabytes, so that data here generated, first shown here, there's roughly either 32 or 64 gigabits per second generated, which might sound relatively small and tame, but that blows up to around 10,000 gigabytes in a single orbit if we are observing for around half of that orbit, which runs away, and we're getting terabytes of data per day. So the plot on the right here is like the worst case scenario. We can never get rid of the data. We just keep gaining data and have to deal with it. The plot on the left is something more hopeful. We find more ground stations. We're able to downlink more frequently, and we're able to get rid of data as we sort of start to get it. Now, the data here is determined by an equation to do with the frequency bandwidth, the polarization, microsampling, and whether we choose to do a 1 or 2-bit quantization scheme, which is really going to determine the quality necessarily of our data being sent back down to Earth. However, it is the trade-off of doubling the data rate. The other potential solution discussed is having in-space links using, instead of dealing with the problems as Ref discussed earlier, there is the potential benefit of being close to the Earth so that we're sending information over a shorter length, which, even though it sounds simple, does matter. We're dealing with less atmospheric interference. We just simply have to use less energy to get all of that information to the ground. However, using emerging commercial solutions, it may be possible at the order of 20 gigabits per second to offload data to relay satellites in low Earth orbit, which can either buffer or immediately send data down to their networks. Now, this is a solution that shows a light combination of SSDs on the satellite, which will hold all of that data when we can. And this is showing a relatively low downlink window. This is assuming that even if we can get a commercial solution, it's going to be pretty bad. We can only downlink for 20 minutes out of 90-minute orbit. All of this goes to show how difficult the data downlink problem is and will be basically forever, given that even with the best technology, there are going to be observation windows that don't work out. And however, it all shows that this is a technologically solved problem and this needs to be worked towards in terms of figuring out what we're doing with the data when.
Okay, thanks, Graham. So that illustrates the severe problem of, we have two main problems. VLBI alone generates a lot of data, but combining that with the low Earth orbit really exacerbates the problem of sending data down to the Earth. And finally, by virtue of the fact that we are in a low Earth orbit, we have to send data down, we have to turn our antenna with a rather aggressive slew rate to maintain line of sight on the same target. This is a very preliminary plot of how fast our antenna has to turn around, our slew rate, but contingent on funding and faculty support, we would be developing these simulations further. So now Sebastian here is going to discuss some of our designs for the antenna and the primary and secondary reflector, and then Luke Anderson is going to take it away with our engineering stuff.
All right, so finally some engineering talk. But all jokes aside, this is our preliminary design for our T-Rex satellite. So during team meetings, with Ref and Luke Anderson, when we were trying to first design the satellite, we noticed that the entire satellite is basically just a huge antenna in space with a box attached to it. So basically, it'll be a 2.5 meter wide dish with a secondary reflector with a Gregorian shape in order to focus the beams coming from the black hole into the aperture, which will then enter right under the dish into a corrugated horn, which basically acts as a waveguide with ridges into it to increase efficiency and polarization. And then everything in the bus of the satellite includes the cryogenic cooler to cool down the system so that the antenna could reach maximum efficiency while observing. And then the onboard computer, and then also attached to the side will be, we're still deciding if it will be foldable or unfoldable, or have the mechanism in order to hold the solar array. That's basically the main idea for the design of the satellite.
Thank you, Sebastian. Okay, great. And let me see if, okay, Luke, so if you'd like to take over our swap requirements, yeah, feel free to, I'll just go through the slides. Yeah, we can hear you. Time must be less than 1 over the orbital velocity times the longest baseline length times the angular field of view. And so that sets these two constraints on the integration time between 67 and 300 seconds. And so now Mia will discuss the basic instrumentation breakdown of T-Rex. Again, this is very preliminary, but take it away, Mia, if you'd like to discuss this.
Yes.
Give us a
This is our
breakdown.
instrumentation breakdown, and it's only for the payloads who want to use this usually the bus, that's the low panels, more off the shelf. This is basically just our science things. We have our antenna here, 2.5 meters, and both that. We saw some of this diagram. The camera earlier. We have estimate this is around material 6 right now. The ultrasonic oscillator, literally, Lisa oscillator is around material 4 right now, broken down. Papers related to that. Our receiver right now is around TRL 8. This is pretty well established technology. Our cryo cooler also, we generously estimated TRL 8 and up to TRL 7. For those of you who don't know, the TRL stands for Technology Readiness Level, which is basically a metric that NASA has for how well things are expected to function in space based on past performance. So TRL 9 is something that has lots of mission history, it's already flown, we know it's going to work. TRL 1 is basically theory, and everything in between is kind of so here you'll be able to see kind of the components within these components, and that's the overall instrumentation.
Thank you, Mia. Okay, so now I'm going to very briefly go through each of these subsystems, and then any questions after the talk, I'll be happy to answer them. And then we'll speak with Michael. Okay, so the antenna, again, so this is a plot of why we selected 2.5 meters for our antenna diameter. Mia can speak to this as well, but essentially we found that we can resolve most of our secondary science targets at an SNR of 5 with a conservative system temperature of 140 degrees Kelvin if our antenna diameter was around 2.5 meters. These secondary science targets, many of them overlap with VEX's secondary science targets. These are quasars or blazars or AGN targets that would be radio loud at around 86 gigahertz. Great. And this is a plot of essentially how long T-Rex would have to integrate for so that we fall below the thermal noise floor of 10 millijanskis. So really, this is the more realistic plot. It assumes a system temperature of 90 degrees Kelvin for T-Rex. And so this is our thermal noise floor. And we can see thermal noise plotted against integration time. And we see that this is the maximum integration time limit, around 270 seconds. This is set by the phase wrap constraint. Anything below that is okay. And we find that around 67 seconds is the minimum amount of time we have to integrate for at a frequency bandwidth of 32 gigahertz to fall below the thermal noise floor. If we assume lower frequency bandwidths, we find that going down to 16 gigahertz for frequency bandwidth, we have to integrate for closer to 200 seconds to fall below the thermal noise floor of 10 millijanskis. But this gives you a sense of the constraints for our integration time. In regards to our cryo cooler, this is a cryo cooler that Luke, Ian, and I we were looking into. This is a pulse tube cryo cooler that can cool down our primary receiver to 15 degrees Kelvin. It sucks up a lot of power and it's very heavy. It's about 300 watts in power consumption and about 30 kilograms after accounting for the cryo cooler electronics. But it does help us potentially achieve our primary science objectives with our thermal noise constraints. In terms of the ultra-stable oscillator, we examined what oscillators would help us achieve a less than 1 degree phase error and less than 10% coherence loss. And the moral of the story is that the JUICE and LISA oscillators would help us achieve those two constraints. I'm going to abbreviate this slightly, but in the interest of time. But and this is the digital backend, which is responsible for converting the analog radio signal into a digital signal, very similar to BEX. And finally, the optical terminal would be some derivative of the T-Bird terminal, which flew in 2023. MIT demonstrated that you could transmit data at 200 gigabits per second from low Earth orbit. So I'm going to cap it off very soon. This takes us to the concept of operations for the T-Rex mission. Let me just bring this down over here. So the T-Rex mission would essentially require 4 kinds of supporting ground infrastructure. Telescopes on the ground that operate at 86 gigahertz that can co-observe with us. This could be Haystack, Green Bank, potentially next generation EHT. Optical terminals to transmit data down to the Earth. Tracking stations that can uplink commands to the satellite, and a data center where all of the information can be correlated. And so if we try to see how this fits together with the Event Horizon Telescope collaboration, this is how everything would come together. I've broken this down. This was inspired by the BEX team's concept of operations, but we have a Science Operations Center that's responsible for identifying the observation schedule of the telescope, and the Mission Operations Center, which essentially relays commands taking into account atmospheric visibility, downlink optical terminal status, and RF station status. And so at the end of the day, the data from ground stations, VLBI telescopes, and the data from T-Rex would all be correlated on the ground. Now, of course, if we're permitted to co-observe with another satellite in medium Earth orbit, then this would add another degree of complication to this concept of operations, but this is the basic idea. And finally, to cap it all off, I'll end with a timeline of what we've done in the last 8 months. So again, this has been a student-led initiative since January, and now we're really trying to obtain faculty expertise from the EHT team, from the BEX team, and from the larger VLBI and radio astronomy community. In January of this year, I had this idea for our next satellite mission, and I reached out to the BEX team and Professor Fleeter here. In February, at that time, obviously, I didn't have anything close to a team. It was, by the way, just me and Graham. So it was just the two of us. And we would read papers from the BEX team every night and kind of share insights with each other. And then in March, Professor Fleeter began to advise us on, oh, okay, well, we got to botch that name. I forgot to change that. In April, we presented at the Ivy Space Conference, and we began corresponding with Luke and Ben. In May, several more undergraduate students became interested, and I trained them to, sorry again about the name, that'll be fixed. But in June and July, we completed the antenna swap requirements and the swap requirements for the main satellite. I was approved as PI for our NASA NIAC grant. And finally, in September, we were accepted by NASA for the NIAC grant. And you can hopefully see that in the beginning. Okay, so this is our proposal. Our funding deadlines look as follows. We are now in the final stage of the NIAC grant. We'll be submitting that next month. We'll be receiving Templeton's decision next month as well. And we're working with our Canadian partners to begin work on the CSA FAST grant. So that's it for our mission. And yeah, that's it. So thank you for your time. yeah, I encourage any questions or strong objections. Okay, yeah, Michael, please.